So this is the 1984 Nobel Prize in Physics, which on the surface is going to sound like it doesn't matter to your life, but I assure you it really does. So the prize was jointly awarded to Carlo Rubbia, who's still alive and with us. He's 90 years old, but he's still alive, and Simon Meer, who unfortunately passed in 2011. I've never had a chance to meet either one of them, but I spoke to some people that actually knew Simon Meer, and he was a very quiet, unassuming guy who apparently just kept working the day after his prize. He's like, forget it, I don't care about the prize. Threw it on a shelf, went back to work. I'm sure he cared, but it wasn't like it changed his life. He was like, oh, cool. Went back to work. But they won for their contributions that led to the discovery of two particles, the W and the Z particle, which are communicators of the weak interaction. This is the nuclear weak interaction. So according to modern physics, there's four fundamental forces at work in nature. The weak interaction is one of those four. And in theory, forces are transported by particles in different ways. Big long particle physics story, but just take my word for that one. And particle physicists don't roast me because we all know it's a little bit different than that, but essentially that's what it is. And the weak interaction is conveyed by the W and Z particles. So Carlo Rubbia proposed and led some experiments that had protons and antiprotons smacking into each other really hard. And when I say really hard, we're talking relativistic speeds. We're not talking like 20 miles an hour versus 50 miles an hour here. We're talking like CERN level fast. And he thought that would lead to the discovery of these new particles, which of course it did. The experiment was run with a whole bunch of people at CERN, but the two that led the project were Carlo and Simon. But it wouldn't have been possible without Simon Vandermeer's techniques for accumulating large numbers of antiprotons inside an accelerator. So without these two guys, it really wouldn't have ever worked. They all came out. One was a theorist, one was the experimentalist, and the theorist was like, "Hey, if we run this experiment where you smack these things together, it'll work." And the other guy goes, "Hey, I know how to do that," and they figured it out. And that did lead to some applications that actually matter. So let's take a little bit of a look here and see some cool equipment and where it might matter to your daily life because it really does. Now, when you deal with particle physics, you deal with large accelerator labs. CERN is one of them. Lots of universities has them. Stanford has a linear accelerator, but the biggest ones are CERN these days. And CERN's always been amongst the biggest of the big. But now, when you deal with those, you get these large, cool-looking pieces of equipment that are pretty neat. But it's only because you need a lot of space to keep these particles kind of flowing in the right direction and kind of get things moving, and they make it go faster and faster and faster and faster and faster until eventually, boom, you get collisions and things go everywhere. So to make antiprotons, you basically take a proton beam and direct it at a heavy metal target, and that causes collisions, and that those collisions generate a whole bunch of particles, secondary effects that kind of come out. One of those are anti-protons, and what you can do is you can funnel them using a magnetic horn to kind of get them to go where you want. You're like, okay, great. Forget all those other particles. I want you guys to go over here and smack into this other stuff because then I'm going to send a second proton beam in and they're going to go boom, and we're going to get these really cool little things that happen inside the accelerator. You're going to be able to detect it, and you're going to see what happens. And what comes out are things like the W and the Z particles that tell us about the nuclear weak force. Big deal, bunch of scientists in the lab. Who really cares, right? It's no big deal. We don't really care much about it. Well, what when you have the weak force is primarily responsible for beta decay, and beta decay gives us a lot of really cool stuff. And inside that beta decay are applications in things like well, you understand nuclear fusion in stars a little bit better. You get medical imaging that pops up, and you can see in the image here, you've got a CT scan and a PET scan. PET scans are what I'm talking about. That's the beta decay side. And when you put those two together, you get a much more clear image of exactly where the problem areas are for things like cancer imaging and whatnot. So it really does give you stuff that makes a difference in our lives because without it, we're saying, doctors might go, well, let's have an exploratory surgery and see what's going on in there. Whereas if you take a CT scan, combine it with a PET scan, which comes out of the beta decay side, which is controlled by the weak force, you then have these fused images. Fused images are more of a modern thing. They haven't really been around that terribly, probably 20, 25 years. But those fused images really allow you to get things to kind of pop to the surface. Other applications of things like cool things like carbon dating and others, but the medical imaging side is really where the nuclear weak force has been put to the most, I think, good use for society. So, it's not just off in a lab we care about these things; they actually do make a difference in the lives and health and well-being and the ability of doctors to diagnose things much more quickly. So, I hope you've enjoyed this video. Doing the 1985 Nobel Prize next. Don't forget to click like and subscribe, and we'll see you soon.